Okay, so this is PHYS1131 and 1141, practice test 2. So we'll present the solution and then we'll look at how it would be marked. So in this first question, we've got a block at rest here. So let's give it mass m block, symbolized like this. And we've got a bullet with a mass m bullet being shot up with some initial velocity towards that block. So this is initial. And then finally, the bullet passes through the block and continues to move upwards. So it's still got the same mass and it's now got some final speed v bullet, but now the block is also moving upwards. So it's got some speed v block. So I'm using capital B for the block here. So that's what happens. This is finally after bullet passes. But in this question, we're asked about what happens to the block. How high does it rise above the table? So after the block starts to move upwards, it's going to keep moving upwards. So this is just as it leaves the table. And it's going to get to some maximum height here where it's going to have V block equals 0. And that'll be our finally. Okay, so there's two things that we're going to have to consider here. We're going to have to consider the collision, and then we'll need to consider what happens to the block after the collision. So let's start with the collision. So during the collision, it is reasonable to assume that external forces are negligible. This means momentum is conserved. So we can write this down as an equation that the mass of the bullet times the initial velocity of the bullet plus the mass of the block times the initial velocity of the block is equal to the mass of the bullet times the velocity of the bullet plus the mass of the block times the final velocity of the block. Now, initially, the velocity of the block is 0. So this term here is 0. And what we're trying to work out is the velocity of the block after the collision, because we know that the initial velocity of the bullet is 1,000 meters per second. We're told that in the question, and that after the collision, the velocity of the bullet is equal to 400 meters per second. So if we know what the velocity of the block is, then we should be able to eventually work out how high it goes. So let's rearrange this equation. We can move this over to this side and write, well, the velocity of the block is equal to the mass of the bullet is common between this term and this term. So we've got the mass of the bullet times the initial velocity of the bullet minus the final velocity of the bullet. And then we'll want to divide by this mass of the block. And now we can substitute into that. So we've got 10 times 10 to the minus 3. The 10 to the minus 3 is to get from the 10 grams. The mass of the bullet is equal to 10 grams. And we want to get from grams to kilograms. And then we're timesing the initial velocity, which was 1,000 upwards, minus the final velocity, which is 400 upwards. And then we want to divide by the mass of the block, which is 5 kilograms. So now solving that on the calculator, we end up with 1.2 meters per second upwards. Okay, so now we know how fast the block is going after the collision. So now we can think about, well, what happens between this time here where it's moving upwards and this time here where it's reached its maximum height and it's come to rest. Well, between those times, there's no non-conservative forces acting. So we can assume after the collision, non-conservative forces do no work, which tells us that mechanical energy is conserved So as an equation, we can write, well, the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. And then looking here, the height above the table is 0. So the initial potential energy, that's 0, but it does have kinetic energy, and we know its speed now, so we can work that out. And then at maximum height, it's come to rest. It's got no velocity, so the final kinetic energy is 0. And so we can say, well, a half times the mass of the block times VB squared, that's the initial kinetic energy, is equal to the final potential energy, which is given by the mass of the block times G times the final height. So we're trying to find this height. The mass of the block will cancel out, and so H is given by a half VB squared over H, which is equal to a half times 1.2 squared over, this should be over G, over 9.8. And solving that on the calculator, I get 0.073 meters, or I can write it as 7.3 centimeters. So now that we've looked at the solution, let's have a look at how it would be marked. So because we were asked along the way to state our assumptions, it's really important that you do that. So we need to say that these external forces are negligible, which means that momentum is conserved. That's worth 1 mark. And then interpreting this as an equation gives us another mark. Now, solving that to get the speed upwards is worth 2 marks. And then we need to consider this second part as the block is rising. So stating that non-conservative forces do no work, which means that mechanical energy is conserved, will give us another mark. And then writing that as an equation will give us another mark. And we'll then get 1 mark for substituting incorrectly and 1 mark for the final correct answer. So part A, I should have put part A up here, is out of a total of 8 marks. This is problem B. So in this problem, we've got a space station which is shaped like a disc. And in the first part of this problem, we're asked about what the required rotation period is in order for people on this space station to feel G, acceleration due to gravity, similar to what we have on Earth. So let's draw a little diagram over here. We've got this space station, which is a disk, and we're talking about a distance d away from the center of this disk, and the disk has a radius r, and we're told that r is equal to 100 meters. And what we want to know is the period. So in order to have an acceleration similar to the acceleration due to gravity, what we need is a centripetal acceleration for a person standing on the edge of the disk like this towards the center, which has the same magnitude as the acceleration due to gravity. So we need that our centripetal acceleration is equal to g. And we know that the centripetal acceleration is given by v squared on r, or omega squared r. So from this, we can work out what omega is, and we know that omega is related to the period through omega is equal to 2 pi over the period. So we can say, well, g is equal to 2 pi on t squared times r. So this tells us that t squared is equal to 4 pi squared r on g. And so the period is going to be equal to 2 pi times the square root of r. Sorry, that r is the radius of the disk here, so it should really be a capital R. So let's put capital R on g, and then we can substitute in. So we've got 2 pi times the square root of 100 over 9.8, so that's approximately 10. But solving that on the calculator, we end up with 20 seconds. Okay, so in part 2 of this question, we're asked to come up with an expression for the mutual potential energy between the ring, which we're assuming has mass capital M, and a point out here with a mass little m. Well, not a point, a mass. So in order to do this, what we can do is consider a little bit of the ring, say down here, which has a mass dm. Now, if I was to sum up all the dm's all around the ring, I'd just get the total mass of my ring, which is m. But let's just consider the contribution from this little part, and you can see the distance away from the center is r, and then this distance is d. So the distance between dm and m here is given by the square root of r squared plus d squared. So we know that our formula for gravitational potential energy is U is equal to minus G m1 m2 on r. So in this case, we could say, well, the contribution to the gravitational potential energy due to just dm is du, and that's going to be equal to minus g. We've got dm, and then we've got little m, and then we're dividing by the distance between these two things, which is the square root of r squared plus d squared. But we're not interested in just the contribution from dm, we want to know from the whole ring. And what's nice about the ring is that every point around the ring is the same distance from this little mass m. So they're all going to contribute in the same way. So we just want to integrate these things, sum them all up. And so we end up with U is equal to minus g little m. When we sum all the dm's, as we mentioned, we get capital M, and then this is over the square root of r squared plus d squared. So part 3 of this question then asks us to use this part or otherwise determine the gravitational attractive force between the ring and the mass. So in order to do this, we can use our equation that the force is equal to minus du dx, where x is the displacement. So how I remember this one is it's like the opposite of the work. So we know that the potential energy is equal to minus f dx, and taking the derivative of that, we can get it into this form here. So for this situation, how we can interpret this is imagine bringing the little mass in from an infinite distance away. It's this distance d here that we're changing. So we can say, well, the force is going to be equal to minus du dd, and so this is going to be equal to minus the integral of dd of u here. We can write u as minus g m m, and then it's r squared plus d squared to the minus a half. So when I differentiate this, the negatives will cancel out each other out. I've got g m m. Now I need to times it by the derivative of what's in here with respect to d, so that'll be 2d. And then the minus a half comes down the front. And then I take 1 off the power, so I've got r squared plus d squared to the minus 3 on 2. So we've got this half cancelling this 2 here, so we can write this as gmmd. We've still got one negative sign left, and we can write this as r squared plus d squared to the 3 on 2. So that is the force. Now another way that we could have done this is to think of the ring and breaking the ring up into lots of little increments, so having a dm here, and then we'd have a dm here, and we could think about how that force contributes to this point here. So this dm will provide an attractive force this way, this dm will provide an attractive force that way, and by symmetry the vertical components here would cancel out while the horizontal components would add. So that would be another way that we could approach this question, but solving it this way would take longer. Now in part 4 of this question, it asks us to show that your answer to the previous question is correct in the limit of very small r. So as the radius of this disk gets really small, if we're some distance away, it looks like a point particle. So as r goes to 0, we expect the disk to look like a point particle. So we expect f to equal g m m over the distance between them squared, so that's d squared, and we expect this to be a force to the left. It's an attractive force, so we end up with a negative there if the diagram was drawn this way like it's drawn in the question. So now what we need to do is look at the limit of this expression. So the limit as r goes to 0 of minus g m md over r squared plus d squared to the 3 on 2. Because d is now a lot bigger than r, we're going to get that this is equal to minus gmmd, and then on the bottom the r is negligible, so we've got d squared, and that's to the 3 on 2. So you can see this will be minus gmmd over d cubed, and so this is equal to minus gmm on d squared. So these are in agreement. Okay, so let's look at how this would be marked. For the first question, either stating it or as an equation or in words that we expect the centripetal acceleration to be the same as the acceleration due to gravity is worth 2 marks. And then going through and solving this to get the period is worth another 2 marks. So for part 2, we get 1 mark for realizing that we need to use this potential energy expression here. We'd get 1 point for realizing that this distance is always the same, however you manage to show that. So I've showed that by substituting it in here, one of those, but you may have written a comment about that. And then we get 1 mark for the final expression. So altogether, this question is then out of 7 marks. Okay, so for this next part, however you've realized that we only need to worry about the force along this axis. So here I did that by integrating over dd, that's 1 mark, but there are of course other ways that you can show that as well, especially if you use this second method. Now there's 1 mark for manipulating the formula correctly. So as long as you make some progress through manipulating it correctly, whichever of the methods you use, you get that mark. And then there's 1 mark for having the correct final answer. Now with part 4, there's 1 mark for substituting r equals 0 into this limit here, or I didn't explicitly substitute it in. I realized that it was very minuscule compared to d squared, so I could just leave it off. So however you've done that, 1 mark. And then 1 mark for comparing it to Newton's law of gravitation, this equation here. And so in total, this question is out of 12 marks. Okay, this is part C. So in this one, Isaac Newton, who, fun fact, came up with his law of universal gravitation while stuck at home because of a viral outbreak, has miraculously returned to Earth, and he's conducting an experiment with an apple in a lift. So let's draw a little diagram to show what's going on. So here's the apple, and the apple is a position H above the floor. So this is H. So let's call the bottom of the lift y equals 0 at t equals 0, and the apple is at y equals H. So in the first part of this question, we're asked to plot an altitude of y against t, showing the position of the floor of the lift and also the apple. And we're meant to go for times before 0 2, so before it's released. So we'll make this our y-axis, and we'll make our t-axis along here. And we've said that at t equals 0, y equals 0. So you don't have to choose that. You could define the height of the apple as 0 if you wanted. But with the lift floor, we're told in the question that it's traveling upwards with a speed v, so it's going up with a constant velocity. So on a displacement time graph, the lift floor is going to have a constant gradient. So we can draw it that way, and the gradient is equal to v. Now with the apple, let's draw that in red. It starts at h, so here's h. Before it is released, it just travels up with the lift at a constant speed v, so that's like this. And then once it's released, gravity acts to accelerate it downwards. So gravity is always acting on it, but gravity takes a little while to change its movement from upwards with the elevator to downwards. So this is going to be a parabolic path like this. So this is the apple, and it's a parabola. Now, part 2 of this question asks us to write an equation for the position of the floor of the lift corresponding to your graph. Okay, so we've got y is equal to vt. So that is 2. And I should just check that this corresponds with y equals 0 at t equals 0, which we can see it does. Part 3 then asks me to write an equation for the position of the apple corresponding to your graph. You need only write the equation for the time of its projectile motion, not before it is dropped or after it hits the floor. Okay, so we're just looking at this part of the graph here. So we can use our kinematic equations for this. The most useful one is S is equal to ut plus a half at squared. S, that's the displacement, so we're looking at the displacement in the y direction here. So this is the displacement from its initial position, and its initial position is h. So we can say initially y equals h, and we also know that the initial speed is equal to v, and we know that the acceleration is minus g, or minus 9.8 if we want a number, because it's downwards. So using this, we can say, well, y is going to be equal to the initial height, which is h, plus vt minus a half gt squared. Now part 4 then asks, showing you're working explicitly, derive an expression for the time when it hits the floor. So the apple is going to hit the floor when the floor and the apple are at the same location. So to solve that, I'll need to have their y's the same. So I'll need y apple, which is what I found in part 3, equals y floor, which is what I found in part 2. So I can say h plus vt minus a half gt squared is equal to vt. Now you can see the vt's are going to cancel out, and I'll have h is equal to a half gt squared. So I'm trying to find the time here. So t is equal to 2h on g, and then take the square root. Okay, so now we've solved that problem, let's go ahead and mark it. So for this first part, the graph, you get 1 point for drawing the lift floor with a constant gradient. So 1 point for a nice straight line here. And 1 point for clearly showing the apple is a distance h above the floor at time 0. So we want this distance here being h, so that's 1 point. 1 point for the apple line at a constant gradient before t equals 0. So these lines should really be parallel. And then 1 point for the apple parabolic path after t equals 0. So 1 point for this. For part 2, we get 1 point for our equation. So something like this. I mean, if your floor was starting at minus h or something, you'd have y equals minus h plus vt, which is another possibility. Part 2 is worth 2 marks. So 2 marks for having this correct expression here. Now part 4, 1 point for realizing that they must have the same y. And then you get 2 marks for correctly solving this. So altogether, this is out of 10 marks.